Hey guys, today I want to present a solution to the Japan Math Olympiad 2023 problem 4. At first, let's have a look on the problem statement. We are asked to find all positive integers n such that n divides phi of n to the power of d of n plus 1 and d of n to the power of 5 does not divide n to the power of phi of n minus 1. 2 days ago we uploaded our 500 subscriber special where we introduced the skill pages on our website. Our first skill page is about number theoretic functions. If you are not familiar with these functions here, you can look it up there. After watching this video, don't forget to check out the subscriber special. Coming back to the problem, our first step is, in order to handle these functions here better, to write down the prime factorization of n. So n should be equal to p1 to the power of r1 times and so on up to pk to the power of rk, where pi are distinct primes and Ri are positive integers. From this prime factorization we can directly calculate phi of n, because we have that phi of n is equal to p1 to the power of r1 minus 1 times p1 minus 1 and so on up to pk to the power of rk minus 1 times pk minus 1. From the divisibility condition that n divides phi of n to the power of d of n plus 1, we directly know that n and phi of n have no common divisors. Taking a look at this representation of phi of n, this directly tells us that Ri is equal to 1, because otherwise pi would divide both n and phi of n. So we can write that phi of n is equal to p1 minus 1 times so on up to pk minus 1, and we can erase the exponents in the prime factorization. Now let's have a look on the value of d of n. We know that d of n is equal to 1 plus r1 times so on up to 1 plus rk, but since we know that r1 up to rk are all equal to 1, this is equal to 2 to the power of k. Therefore, our second condition here tells us that 2 to the power of 5k does not divide n to the power of phi of n minus 1. This motivates us to have a closer look on the number of times 2 divides the expression here on the right hand side, because this condition here tells us that 5k is greater than nu 2 of n to the power of phi of n minus 1. We want to use the LTE lemma for the prime number 2, but here we have to watch out because there are two different cases which depend on the parity of the exponent phi of n. If we have a look back onto the representation of phi of n, we see that phi of n can only be odd if all these factors here are odd, but this is only possible if all the prime numbers here are true, and therefore the only possible case for phi of n to be equal to an odd number is if n is equal to 1 or n is equal to 2. So let's have a quick look on these two cases, and after that we can go on with our main proof and can assume that phi of n is even. If n is equal to 1, we see that the right hand side here in this condition is equal to 1 to the power of phi of 1 minus 1, which is equal to 0, and therefore this condition can't be true because everything divides 0, so n equals 1 is no solution. For n equals 2, we get that 2 must divide phi of 2, which is 1 to the power of d of 2, which is 2, so this right hand side here is 2, so the first condition is correct, and for the second condition we have that d of 2 to the power of 5, which is 2 to the power of 5, should not divide 2 to the power of phi of 2, which is 1 minus 1, so the right hand side here is equal to 1, and this clearly holds, and therefore n equals 2 is a solution. Let's go on with the case that n is greater than 2, and here we can assume that phi of n is even, as I already said, and therefore we can now use the LTE lemma and get that this is equal to nu 2 of n squared minus 1 plus nu 2 of phi of n minus 1. In order to find out more information about nu2 of phi of n, we want to have again a look at our first condition, which is now that n divides phi of n to the power of 2 to the power of k plus 1. This tells us that phi of n to the power of 2 to the power of k is congruent to minus 1 modulo pi for every prime number which divides n, and this also implies that phi of n to the power of 2 to the power of k plus 1 is congruent to 1 modulo pi. Thus, the order of phi of n modulo pi does not divide 2 to the power of k, but the order of pi of phi of n must divide 2 to the power of k plus 1, and therefore the only possible value for the order of pi of phi of n is that it is equal to 2 to the power of k plus 1. Moreover, we know that the order of phi of n modulo pi divides pi minus 1, and therefore we know that 2 to the power of k plus 1 divides pi minus 1, or nu2 of pi minus 1 is greater than or equal to k plus 1. From this inequality here, we can bound nu2 of phi of n from below, because we know since n has exactly k prime factors, this must be greater than or equal to k times k plus 1, and nu2 of n squared minus 1 can be written as nu2 of n minus 1 plus nu2 of n plus 1 and the minus 1 in the end. We can also bound nu2 of n minus 1 from below, because since we know that pi is congruent to 1 modulo 2 to the power of k plus 1, and since n is the product of the pi's, we also have that n is congruent to 1 modulo 2 to the power of k plus 1. Therefore, we know that nu2 of n minus 1 is greater than or equal to k plus 1. So the first term here can be bounded by k plus 1 all squared, and moreover we know that n must be odd, and therefore n plus 1 is even, so the last term here is greater than or equal to 0. This inequality here is false for k greater than or equal to 3, which you can check by your own as a small exercise, and therefore we can conclude that k must be less than or equal to 2. We start with the case that k is equal to 2. Here we see that plugging in k equals 2 tells us that this inequality is 10 is greater than 9, which is indeed true. But if at some point where we make a bound, the bound is not a perfect bound, so for example this bound here is not perfect, and we have that this equation here is greater than this one, then since we work in the positive integers, a greater sign implies that a term is greater than or equal to another term plus 1. And this would yield a contradiction here, because if we have not a 9 on the right hand side, but a greater positive integer, then this can't be true. Therefore, at these 2 points here, we must have equality. Moreover, since this inequality here comes from the fact that nu2 of pi minus 1 is greater than or equal to k plus 1, we must also have equality here for every pi. So if we write n equals p1 times p2, we get that nu2 of pi minus 1 is equal to k plus 1 for I equals to 1 and 2. Here we have that since k equals 2, this is equal to 3, and therefore we get that p1 is congruent to p2 is congruent to 9 modulo 16. This tells us now that n, which is equal to p1 times p2, is congruent to 9 squared, which is congruent to 1 modulo 16. Hence we get a contradiction, because in the second bound here we bounded nu2 of n minus 1 by k plus 1, but we see that nu2 of n minus 1 is at least 4, and therefore this bound here is not strict, and therefore we have a contradiction. For k equal to 1, we get that n is equal to p prime, and here our first condition tells us that p divides phi of n, which is p minus 1, to the power of d of n, which is 2 plus 1. Multiplying the first summand out, we get that this is equal to p squared minus 2p plus 1, so plus 2, and therefore we get that p must divide 2. We remember that n is greater than 2, so p is greater than 2, and therefore this is clearly a contradiction. So in the case k equals 1, we also have no solutions, and the case k equals to 0 is already done, and therefore n equals 2 is our only solution, and we are done.